So, all right. So where were we? What we said was that we are going to look at this extreme, the Reynolds number tending to infinity, or if it is some other system like controlled by Rayleigh number tending to infinity, where the velocity on vector seems to follow extremely complicated time and space dependence. So this is this is just, let's say, the phenomenological observation, and what we were trying to see is that whether one can make any sense of anything in this region, and the two things which are going to be, I mean, if one wants to be quantitative, then obviously there is the incompressibility condition, which is divergence V equal to 0, and there is Navier-Stokes equation, which says that del T V plus V dot grad on V is minus gradient of P set rho equal to 0, and that's the that's without any external forcing. So any and if there is external forcing, I'll just have to add that on. And so any a really quantitative issue has to fall back on these two equations over here, where, I mean, these it's actually, you incorporate this into this by taking a divergence over here, which tells you that del square P is del beta V alpha del alpha V beta. So that's tells you what P is, and you can substitute this back, and what you are looking at is another term of this kind. So very good. So these two terms are really more or less on the same footing, and the momentum, writing them in momentum space, as I said you should try out, makes that very clear. We'll come to that in a moment. But then, I mean, given this, what's the difficulty with working with these equations? The difficulty comes from this nonlinear term over here, which is very difficult to handle. And so that's the technical difficulty, which has ramifications, as we'll talk about. But then, I mean, what is the problem? The problem is we are making a statement that VRT is basically a random function, and if there is if we are talking about a random function, then I should talk about probability distributions. And so the chap whose probability distribution you look for is somebody who is from whom you have removed the inhomogeneities in the system, and this chap summed over x vectors and accordingly normalized. So that's your delta V alpha over R, which is the random variable that one looks at. In principle, you should be able to calculate delta V alpha over R, of R. And the reason you want to calculate it, that in this something called inertial range, in inertial range, this P is universal. So question is, what's the inertial range? The inertial range was the picture that one built up was that the overall energy balance says that the time derivative of the kinetic energy is minus del alpha V beta square d3r. So if t goes to infinity, Ek would have to go to 0, which means all motion would stop. So you prevent that by having some kind of forcing term come over here. So you add a forcing term which can supply energy to you, and so you write this instead as minus nu this plus some external forcing, which is this d3r. And in the steady state, these two chaps are equal, so equal to 0 in overall steady state, and this dissipation rate is generally written as epsilon, and so is this energy forcing then. And then you ask for what is the scales where dissipation and injection are operative, and you find that this is operational at a small scale L, which can be determined in terms of nu and epsilon. This is at large scales L, which is determined by the mean flow velocity and epsilon. And this ratio L over L is Reynolds number to the power 3/4. So as Reynolds number tends to infinity, L over L is much greater than 1. So you have this whole set of scales where which are far away from source and sink. So energy in over here and dissipated over here, and in between are these R's over here that one is talking about. So L much smaller than R, much greater. Small L much smaller than R, which in turn is much greater. And this is not a hypothetical region anymore. It's in the very large Reynolds number. It is something which can give you a few decades. And so in this few decades, that is where things are universal. So this universality links up to over here. And in that range, says Kolmogorov, that if you raise this to the power n, then you will get some coefficient constant n, and epsilon to the power n by 3, r to the power n by 3, where which a result which is obtained purely by dimensional analysis. So this is where we were, that there is this also in d equal to 2, where there is something the energy is for n equal to 2, where energy is a very meaningful quantity. This means that energy is proportional to k to the power minus 5 by 3, and that's the Kolmogorov 5/3 law. So this is where we were. Now the one thing which this universal, it looks like super universality, that it should be valid in all spatial dimensions, d equal to 2, d equal to 1, and what have you. So first comment has to be that is there really, I mean, this question of is this argument valid in arbitrary dimensions? And then you have to, so if you are particularly in d equal to 2, let me tell you that there are problems and further interesting sidelines develop from there. So at least that is something you should be aware of. Now, to understand the d equal to 2 problem, one has to once again come back and see what the business, what's the issue over here? What happened? What happened was that I had a conserved quantity, Ek conserved, if nu is equal to 0. So there is a conservation law of energy when nu is equal to 0, and then this Kolmogorov picture is that all right, this conserved, in reality there is some viscosity operational at very small scales, so it will dissipate things over there. But then, I mean, that would mean this steady state condition would mean that there has to be energy coming in, and so this conserved quantity, when you add in this viscosity and forcing, the conserved quantity flows, has a flux from the large scales to the small scales. Now this is very let's say a general point of view, that if I look at a conserved quantity in some limit, then put in factors which are going to dissipate it or make it grow or do something to it, and then if I want a steady state, then I'll have to do the reverse at the other end, and I can imagine that there is a flux which this picture tells you about. So this assumption that there is a cascade, which takes you from these scales to these scales, and that, mind you, is what the nonlinear terms in this equation are doing, is a consequence of number one, the conserved, that first you find out that in a inviscid limit there is a conserved quantity, and then you look at the issue of whether that conserved quantity can be dissipated at some scales or what, and then try to set up a steady state. So all right, so d equal to 2. Obviously what we said over here remains true. But then d equal to, there was a quantity called vorticity, which was the curl of V, which we talked about quite a lot in the first couple of days, but I never told you what is the dynamics of omega. So the dynamics to find from this Navier-Stokes equation, I need to take a curl and get the Navier-Stokes, get the dynamics of omega out, and that second term which I had over there, V dot grad of V was written, could be written as half gradient of V square over 2 plus omega cross V. So that's an identity that we had done, and that gives you the picture that del t omega. So if I take a if I take a curl of that equation over there, this curl is a gradient, pure gradient curl goes away. So plus curl of omega cross V. The pressure term is a pure gradient and that goes away, and then it is nu del square omega. Now what is this? Playing around with these cross products, you would find that this is writable as this omega minus omega dot del on V. It's this. So just the identity of A cross B cross C, and you have this. Aha. So now the point is D equal, so this is in any dimension. So D equal to 3, I never talked about it because all that it meant, I would have this term, additional term to worry about, and all right, I mean if I can solve for V, I can get the omega, not much percentage in talking about omega equation as such. There can be times when it's worth talking about, but less. But let's talk about D equal to 2. D equal to 2, and this part is valid. D equal to 3, 2, what, and so on, higher than somewhere between 2 and 3 or wherever the omega can be generalized as with Levi-Civita symbols and whatnot. But and anyway, D equal to 3, 2 certainly valid. But then it is the coordinates are in D equal to 2 is x and y. So what about what happens to omega vector and in D equal to 2? So is omega still a vector in D equal to 2? That's the question. Does omega have 2 components? 3? How many components would omega have in D equal to 2? 1. So there is just one component, and that is del, give or take, so this is del x, del x of Vy minus del Vx. Okay, so that's why there is just one component. Very good. Now omega in D equal to 2, so this, and what would be the direction of this so-called direction? If this were a 3-dimensional space, the direction would be in the z direction. So this omega is a sort of pointing out of this plane. So omega dot del times V is, it's a 2-dimensional system, 0. The del operation is in the plane, omega is perpendicular to the plane, so out goes this chap. So del t omega plus V dot grad on omega, dropping the, is this. So this is your, and therefore if you now do calculate del t omega square d2r, this integral, this would be minus nu integral grad omega square d2r. This term would vanish for the divergence-less flow exactly as it vanished in d equal to 3. And so the omega square so omega square is a conserved, omega square conserved in d equal to 2. So you have additional energy is obviously conserved, but you have a additional conservation law in d equal to 2. This quantity over here is called the entropy definition. So this is called the entropy. So in the inviscid limit, the entropy is conserved, and in the planar flow. So d equal to 2, and this is so now at very small scales, there if I put in viscosity, this is going to get dissipated. So I assume that this chap is getting dissipated at very small scales. Now omega is a gradient of V. So if this integral is going to be finite at these very small scales, then the other chap, this one over here in d equal to 2, that is going to remain finite, because if it is a more singular object than velocity, which is going to become at small scales, the omega is more singular than the velocity. It is omega square d2r, which remains, gives you a number. But if that just gives you a number, then this chap is going to give you 0. So there is going to be, in this case, the flow from large scales to small scales would have to be that of entropy. But what about energy? Energy also has a conserved quantity. That too should be flowing, but can't flow in the forward direction. There is some theorem in d equal to 2 called Yotford's theorem, which essentially tells you that if the or rather, which can, let's say, the correct thing would be from that with a little ifs, a few ifs and buts, you can argue that if entropy flows in one direction, then the energy has to flow in some other direction. The arguments are a bit tenuous. You bring in some out of the blue, some equilibrium distribution and so on and so forth, and all right, I mean, but I really don't want to get into that. But the part which is very clear is that if I have the viscosity in, and this chap is going to do my dissipation for for the entropy, then if the velocity field is such that the entropy is being dissipated, so this chap is big at small, then if this chap is big, then that is this integral has become significant such that small nu times that is finite. This chap is not going to be a problem, so there is no reason for the energy to flow in that direction. But there can be a flow. Energy is also a conserved quantity, and the energy, so the entropy flows in from large length scales to small length scales, and the picture is that energy flows in the reverse direction, so there is a backward cascade of the energy. You can ask yourself what in the world happens to this energy, where does it go and settle? Well, that's it goes into these large eddies, and at various times in history, various interesting things like BC and so on and so forth have been conjectured for what goes on at to the energy which seems to be piling up at the large scales. My personal bias is sort of all right, flows, but then what happens? Let's not get into that. So in any case, I mean, personal bias or not, I mean, not that there is time to talk about it, but this picture should be true, should be clear that d equal to 3 is not the same as d equal to 2. So this Kolmogorov picture is not that when we talk about this universality, it is not this super universality which is independent of spatial dimension, but the universality breaks in a very interesting fashion that I'm supposed to look at the conserved quantities and you can also check all the powers of entropy are conserved, gives you a whole set of them, conformal invariance and things like that enters the picture and gives 2D a lot to do. Maybe Shumit next week, I mean, whatever and certainly the conformal invariance seems to be on the agenda. So, all right, so that's the comment about d equal to 2. So now back to hereafter, we'll stick to d equal to 3. That here is this. There are a couple of issues that one would like to address. That it's the, after all, I mean, this based on Navier-Stokes equation, can you go some distance? And the point is, what would be a starting point for getting going? Now, the point is that we have been talking about a velocity field with this external force over there, because to maintain the steady state. Now, when we looked at the breakup yesterday of the mean flow and the fluctuating flow, then this fluctuating flow had a contribution from the mean flow with terms that look like u and some u alpha del alpha v. And this is your random part over here. So this was a additional term. So the force, the coupling between the mean flow and the turbulent flow gives rise to an additional right hand side which has things like this. And they are all that have, all of them have entered in some collectively in this external force over here. So the point that I want to make is that it is not at all a bad idea to consider this force to be a random force. Now, there are, I mean, issues over here, issues like that after all, it's a deterministic system without this f over here, which becomes turbulent, which becomes complicated because of the nonlinear term over here. That deterministic system can become problematic is people did that all through the 80s and 90s, and so the so-called chaotic behavior of dynamical systems and tells you that you can get random behavior, that is extreme sensitivity to initial conditions, and therefore for all practical purposes random behavior through the deterministic part. So why, but that would be impossible to calculate. So just from the practical point of view, to make life simple, it is much better to have a random force in over here. It is not so unrealistic because the, as I said, the coupling between the mean flow and the turbulent flow does have a random component in it. So it is worth your while to put an additional random force over here, And now you see what you are staring at is something which looks like, I mean, suppress this part over here. You have a Langevin, simple linear Langevin equation. You have the whole machinery that people have been talking about through this week at your command. But then, just by having this force over here, and it becomes probably a more tractable issue. So the force, for this force, I have to tell you what the correlation of the force is. I have to specify the statistics of this force, and you give the random function correlated Gaussian distributed external force R1 T1 F beta R2 T2 expectation value is some function C alpha beta of R1 minus R2 translational invariance and delta of T1 minus T2. So there is a spatial dependence, some kind of spatial dependence in this in this part over here, and the time part is the standard white noise, your delta function of T1 and T2, which you have been seeing from day one over here. So you specify and the higher order correlations come from the fact that it is Gaussian distributed. So all correlations of F known, and thereafter you should be able to work this through. So now what's the technical problem? The technical problem is exactly what Abhishek mentioned a few minutes ago, that if I want to get the 2-point correlation function, then this term over here will relate it to a 3. So 2 V's correlated would be related to 3 V's which are correlated, and then the 3 V correlated would lead to a 4 V correlated, and therefore I have a problem where that n-point function is determined by the n plus 1, and so you have a problem. So that's the technical problem, which remains the same for everybody, and but all right, at least maybe it gives you a ground for getting started. So at least, so all right, so this is what in literature goes under the name of randomly stirred fluids. So randomly stirred fluids, the external force is absolutely essential in view of the fact that I want a steady state, and it is make it random. That's as I said, is not particularly a crime. All right, now what? Having done that, what now? Why? I mean, given this, people educated in dynamic critical phenomena, KPZ, so on and so forth, and I would say maybe there is a renormalization group which it's tailor-made for applying renormalization group techniques. Now you see here comes the technical problem that we are. Where am I supposed to see scaling behavior? So scaling behavior is supposed to be seen in this inertial range over here. Critical phenomena, the other standard place where you where it all began, you saw scaling behavior at very large distances, large compared to what? Large compared to the lattice spacing. If you were thinking in terms of Ising, you were worrying about large compared to lattice spacing, and if you were thinking of continuum, maybe large compared to interatomic spacings and things like that. So critical phenomena asked for scaling provided R was something much greater than A. And that's the region in which you are interested in KPZ scaling. Also has asymptotic region. So most of the systems where all the systems where our renormalization group works has a single scale, and you are looking beyond it and at much larger scales, and so you do this removal of degrees of freedom, and you get. But here you are stuck. That's a miserable failure. And the point is that you can, in this way, look at scales which are much, much greater than the scale small l. There it is going to give you a set of answers, and the people who very carefully wrote down these models in the 70s, starting with Forster, Nelson and Stephen, followed up by for fully developed turbulence, De Dominicis and Martin, in the very early days made it very clear that what they were talking about was large distance, long time properties of stirred fluids. Under certain conditions it gave Kolmogorov, but those early studies absolutely made it clear that it was not. It was a curiosity that it gave Kolmogorov in some under certain conditions, but it was not really the inertial range which Kolmogorov talked about. So now now where does this problem technically come up? Say, let's say if you were to use this the distribution function of the force over here to set up the standard functional integral description, the Martin-Sigia-Rose kind of thing. So you could set up a field theory by making use of the distribution of this f and converting it to a functional for this velocity out of which. But that field theory is not renormalizable when the spectrum is Kolmogorov. So, and once again the lack of renormalizability over there is linked with the fact that there are two scales in this problem, and therefore life is very bad. So the summary of what I'm trying to say is that the conventional techniques which in continuum problems and in discrete problems when like I have given are not exactly successful over here. You still try and you do this, you do that, but at the end of the day you might not have. Which is basically the way I think. I mean, so all right. I mean, there are, at the end of the day, that's the way which everybody must be thinking about it. Otherwise, there wouldn't be a problem. So, all right. But then, in this, what kind of constraints can I put on this system? What statements can be made with some amount of confidence? Well, let's look at the fact that I want anything which looks like V with R1T or any power of that, and this is some R prime T. This kind of a correlation equal time. So I want it to be this quantity to be time independent. So I want to impose what is known as stationarity That is, all these correlation functions that I have been talking to you about, these Kolmogorov things, like they are delta V as a function of R, and they are all at the same time t, and they don't depend on t. So these are all stationary answers, and so there is no t dependence over here. At all times you can see this chap. So the point is, there is stationarity, and maybe as a first go I should try and see what stationarity is all about. For example, I should be looking at V alpha x t, V beta y t should be equal to V alpha x t plus delta t, V beta y t plus delta t. So these two things should certainly be the same. So there is that is a constraint, that is a condition that this evolution should satisfy. So can I write down? Right. So I'm looking at del t V alpha is minus V beta del beta V alpha minus del alpha p plus nu del square V alpha plus f. I'm going to integrate this. I'm going to integrate this from integrate from t to t plus delta t. So I'll integrate from t to t plus delta t, and then on this side over here I'm going to get V alpha delta t, so all this at x. So I'm going to suppress the x right now, minus V alpha t. So this integrated gives me this over here, V alpha t plus delta. So the left hand side, multiply the integrate the first term over here. It's a well-behaved term. So this well-behaved term over this short interval, I can just replace it by the mean value, so do the mean value theorem and write this as V beta del beta V alpha times delta t. There would be corrections which would be like delta t squared, delta t cubed, and so on and so forth. So mean value theorem would ensure that the leading term is delta t. Then there are terms of order delta t square, which, as we have seen, we don't need to worry about. I mean, for the same reason that one did not have to worry about in all the derivations of Fokker-Planck and so on that you have seen. It's absolutely for the same reason we don't have to worry about it here. So then it is the next term, which is this, and that multiplied by delta t, same, and this plus ordered terms over here, plus nu del square and V and alpha, and then once again times delta t. And now comes integral t to t plus delta t f x t dt. Now these I could summarily deal with. Here, this, you know the answer. that t2 t plus delta t f x t dt, what would its dependence be on delta t? 1 by delta see, and order of, no, there is a delta function in the correlator over here. So that I mean we have been listening to this all through the last few days, that this is this random noise over here which has this correlator which is delta of T1 minus T2. So there has to be in the strength of this f of x t is extremely big when the interval becomes small. So how big? 1 by delta? 1 by root over delta t. So because it is the 1 by delta t comes from the delta function over here, but the two of them give you 1 over delta t. So each one of them is like 1 over square root of delta t. So this term over here, I better make sure that this term is of the order delta t to the power half, right? So all the others I have got are like delta t, but this one is delta t to the power half. Good. So that's the now the interval gives you delta t and the yeah. Delta t that has v beta t and similar terms over here. So comes the first term from this part, multiplies this, that's certainly something that we'll have to keep, which is just this term over here. Then it is this multiplied by this, which is of order delta t, this multiplied by this, which is of order delta t, this multiplied by this, once again of order delta t, this multiplied by this is something which looks like is going to be, if I write it explicitly, is v beta t to t plus delta t f dt, but is expectation value average f is equal to 0, and therefore that term will not show up after taking the averaging. So average out, and then the average of f is 0, f so all is Gaussian distributed, and so all the so that's why this is not going to show up. So what is going to show up? So V alpha now comes is, so I'm writing the right hand side, I get exactly this chap over here, then I get this multiplying first term from this part multiplies this, that's certainly something that we'll have to keep, which is just this term over here. Then it is this multiplied by this, which is of order delta t, this multiplied by this, which is of order delta t, this multiplied by this, once again of order delta t, this multiplied by this is something which looks like is going to be, if I write it explicitly, is v beta t to t plus delta t f dt, but is expectation value average f is equal to 0, and therefore that term will not show up after taking the averaging. So average and out, and then the average of f is 0, f, and so all is Gaussian distributed, and so all the so that's why this is not going to show up. So what is going to show up? So V alpha now comes is, so I'm writing the right hand side, I get exactly this chap over here. Then I get this multiplying the bad notation is here. Good. So it is then plus delta t and no, minus. No. So it is minus delta t average of V beta y V gamma del gamma acting on V alpha x. Yeah? Right? Done? So V beta y and this is. Next is minus delta t, and it is V beta y, and it is del alpha p and x. That. There is going to be plus nu delta t V beta y del square V alpha x, and then what is left? So this is then plus the reverse thing, terms where x and y are interchanged, right? I mean this chap multiplying the corresponding chaps over here, and one more term of order delta t. That is the term which is this multiplied by the corresponding term over here. So the FF correlator, right? So plus the term which I have to keep, it is t plus delta t, this f x t f y t Good. So that's the, so this is the thing. Now this has cancelled out this chap over here. Now let's and that's the general condition for stationarity. So this is the constraint, that the fact that I have a stationary process puts this constraint on me. So I'm going to, this is true for all alpha and beta. I'm going to look at the special situation where it is alpha equal to beta, will make life simpler. So now this equation over here is going to give you C alpha beta and this So it's F alpha over here, it's F over there. So it's going to give you this C alpha beta R1 minus R2, the delta function. One of the time integrations takes care of the delta function, the other time integration gives you the delta t. So so that's going to be the C alpha beta R1 minus R2, and when I set alpha beta beta equal to alpha, it's C alpha alpha. So alpha equal to beta tells me that V alpha y V beta del beta, so on V alpha x, that taken to this side, plus x going back and forth to y. Now comes this with V alpha del alpha, so so this is alpha, so it is this term when it becomes V alpha y del alpha p of x. When I'm looking at this chap over here, then the function, all correlation functions which look like something of x times something of y, that because of translational invariance has to be a function of x minus y. So this chap is so I can take this differentiation which is with respect to x, I can take it outside. So here is the sequence of steps. This is a derivative with respect to x. Step 1, I take it outside. Step 2, I argue that the correlation function that I'm seeing over here is a function of x minus y. Step 3, I then notice that a derivative with x is within given a sign the same as derivative with respect to y. Step 4, I bring this now back on the v over here, and divergence free gives me 0. Yeah, so that's the that's a sequence of events which one plays out repeatedly in problems like this. So that disappears. So this is equal to nu, and then it is, so this has gone to the other side, and so it is this it is V alpha y del square V alpha x, and it is plus this as something of x minus some c of sorry, there has, this part has to have x to x going to y plus some c which is a function. This is it. All right. So this is the stationarity condition in the special case when alpha is equal to beta. So very good. What am I looking at? I'm very close to the finish, but still a couple of things to clarify. Very good. So let me, so this is all, let me write. V alpha y. I'm looking at this term and trying to work on it. same step 1, exploit divergence V equal to 0. Yeah. So that then it's a derivative with respect to x. So bring it out. So this becomes this because divergence of V is 0. Now take the beta out. So it is del beta. This is with respect to x. This part of it is a little that continuously one has to remember what is with respect to what. So it's a derivative with respect to x of a 3-point function which looks like, or rather a 3-velocity function at 2 points. So V alpha y, V alpha x, V beta x. Are all of you comfortable up to this point? Yeah? It's, I mean, it's just been standard manipulations so far, really nothing which has, yeah? All right. Now, look at this. Let me look at a C alpha beta gamma. So you are happy that I need to that I have this term. Look at, see, these two chaps are not going to be. You can see what these two chaps are. This is the dissipation. Yeah. So this is the dissipation and nothing much to worry about. This is obviously the amount of energy. That's what it will turn out. The amount of energy that you are feeding in. So nothing to worry about with those. So it's this alone which we need to put it in a form where I can relate it to Kolmogorov in some way. So if I want to relate it to Kolmogorov, I want to look at U alpha V alpha x minus V alpha y, that into V beta x minus V beta y into V gamma x minus V gamma y, and the expectation correlation function of that. So as we have seen, this quantity can only, there is a question of the translational invariance, there is a question of rotational invariance, and therefore the only vector which is relevant in this problem is the r vector which is equal to x minus y. That is, out of the components, this tensor C alpha beta gamma has to be formed out of the components of the r vector, which is, I mean, to get dimension, leave out dimensionalities. Let's just talk about the unit vector in the direction of r. Whose magnitude is x minus y dotted with r. So the unit vector in the direction of r, so r vector divided by r, that's what it is. And so it is out of the components of this unit vector n alpha beta gamma, n alpha n beta n gamma, that you need to formulate this chap, and you have to help you the delta functions, the delta alpha beta. So, delta alpha beta and the n alpha n beta n gamma has to give you the structure of this function over here. So, you can write down the structure as something into delta alpha beta n gamma plus something into delta alpha gamma n beta plus something into delta beta gamma n alpha plus something into n alpha n beta n gamma. Is that clear? Right? Huh? So, question 1, if it is, if you have agreed that it is right, I mean, it's always dangerous. The first term over, so imagine I have multiplied out this, and yeah. So imagine I have multiplied out things in this C alpha beta, and I have developed the written out explicitly the different terms. Equals so then let's look at V alpha x, V beta x, V gamma y. So, I have taken this, this, and I have taken this. So, I have multiplied this with this as I had done before, and then now inside I have taken this. Very good. Now, look at the corresponding V alpha y, V beta y. So, V alpha y, V beta y, I have multiplied that, and there is this which is V gamma x. Right, V alpha y, V beta y, and then V gamma x, and the other was V alpha x, V beta x, and there was a minus sign here. So, I should have kept that minus sign going, so that minus sign over here. And so, I have these two terms. Now, what do you have to, what can you tell me, looking at that same chap over there, what can you tell me about this fellow? So, how are this and this related? Equal, averages are what we are. Equal or subtle difference? I mean, that is, are you telling me equal of without the minus sign or with the minus sign? Without the minus sign. Then they add up to 0. See, what have I interchanged in these two? I have interchanged x and y. So, in one case, if it is a function of x minus y, the other would have to be a function of y minus x. So, what should be the relation between those two? Negative of, yeah. So, one is the negative of the other. So, there are 8 terms over here multiplied out. 2 of those chaps are 0. That is, this multiplied by this is 0. This multiplied by this is 0. So, there are 6. Of the 6, pairwise they add up. And so, I have this identity So I have the identity that C alpha beta gamma equals 2 times V alpha, I want to go with the positive signs. So V alpha y, V beta, V alpha y, V beta y, V gamma x plus V alpha y, V gamma y, V beta x plus V, so alpha beta alpha gamma, the other has to be beta gamma. So beta y, V gamma y, V alpha x. Yeah? So that's the general relation that I have. So I have this identity. So what what all this started out because I wanted to get a handle on this one. Now this, I have got terms like this. I have got 2 x's, or in that case 2 y's and 1 x. I had 2 x's and 1 y, and I have written it, I mean just interchange x and y and life would be all right. So I have got something, except that I have got it with alpha beta gamma. I didn't need it. I needed only a alpha beta. So in this business over here, I am interested only in setting alpha equal to so the part where alpha is set equal to gamma. So it is alpha beta alpha. So gamma set equal to alpha, and then this is going to be 2, and so alpha set equal to gamma, that makes it alpha and this gamma over here, which is going to be the same as, so these two terms will become the same. That is, I will have 2 times V alpha y, V beta y, V alpha x, right? That's this one, and that's the same as that one when I have set alpha equal to gamma. Yeah. And then I have one of this, which is V alpha y, V alpha y, V beta x. Now you want, so what is it that I have a derivative also over here. So it's the derivative that one is interested in, not the thing itself. So as written down here, it was, I mean, this alpha with a x and y, and then it's a derivative with respect to x, which occurs with alpha and beta. So it is that derivative that is with the alpha, the two differ. So it is the derivative with respect to what is a derivative with respect to x over there. The corresponding thing as written down over here would have to be a derivative with respect to y, but that's a small issue. The point is, now I take a derivative with respect to y, and when I take a derivative with respect to y over here, this chap will disappear, and finally I have this result that del with respect to this y vector over here of this C alpha beta alpha is 4 times the chap that I had started out with. So the thing which I wanted, this del including the del thing, that whole thing over here is just the whole thing over here, and that is related to C alpha beta alpha which is defined. So this is the identity. Now we are through. So after this, there is very little that needs to be done. Sorry, it is alpha beta alpha. So you set it alpha over here. So this becomes V minus, so C alpha beta alpha so I'm looking at C alpha beta alpha, that's equal to V of x minus V of y whole square times V beta x minus V beta y. So there we are. So alpha beta alpha is Vx minus Vy whole square, V beta minus this, and there is a derivative which is with respect to this value. And this derivative, so that's the term that I have been playing around over here. So this term which I have been using is just 1 over 4 and then a derivative with respect to y of this quantity which is square of this difference times this V beta x minus. So that's the, now then I'm through the vital point. So there is x to y and y to y, that's not important. The thing is that now you see I can take, I'm interested in the limit of x going to, I'm interested in taking 2 limits. That is no sum of the components of y over here with the free component over here. That's what I meant. It's just a derivative. It's a gradient and not a divergence. That's what. So now what? Now the point is that I'm interested in 2 limits. One is nu tending to 0, which is Reynolds number tending to infinity. And then I want this difference r to be small. So I want x minus y tending to be 0 to make my r small. So I'm interested in 2 processes over here. 2 limiting processes. One make x go to y and the other is make nu very small so that the Reynolds number becomes very big. Suppose I take x going to y first. So I take x going to, so I do x going to y first. If I take x going to y first, there is Vx minus Vy whole square over here goes to 0 and then it is this term over here which is left, which is del square V alpha x, V alpha now x. You can play around with the derivative, shift it to the other side, so it is gradient of V square. So that's the dissipation rate. So I take, and then it is the dissipation rate epsilon, which is equal to C of 0. So that's the balance, that this dissipation rate over here is the forcing produced by the external Now comes the next chap, that it is nu tending to 0 first. So nu tending to 0 first, and then it is x going to sorry, that's what did I do? It is nu x yeah, okay. So it is x going to keep this for the time, x going to y first, and this term is gone, and now it is this chap over here. Now, what has this told you? Just wanted to make this comment before I go on. That I'm getting this x tending to y. So this chap over here, it is nu tending to 0, and there is this gradient of velocity over here, and I'm saying that as nu tends to 0, the velocity field is such that it is nu, and then there is this grad v square, and that tends to some finite number epsilon, which tells me that the v, at least in the sense of not all derivatives finite, is not analytic at very small values. So v is a singular function in the sense that not all derivatives can exist at very small distances, and that is why this square over here is becoming infinitely big, while nu is going to 0, and the two together gives me a finite dissipation. So this is the so-called anomaly, that as nu goes to 0, your velocity field becomes non-analytic and gives some gradients to be infinitely big and gives you a finite answer. So all right, great. Now take nu going to 0 first. This drops out. This drops out, and then it is this correlation. Now take x going to y going to x. So this is going to be some small difference over here. So this is done. Now take nu going to 0 first. So nu going to 0 first, out goes this, and then this chap over here is 1/4 so if I shift to, I have written this as del v del x, so I can shift to del x, and that will bring a negative sign, derivative with respect to x, and then it is this square times v beta, so v beta, let's say x minus v beta y. Looked at this over here. It's a minus sign. If I had a y, I make it a minus, so that's minus. That's equal to c of 0, which is equal to epsilon, and that's this. And therefore, you can see that the v minus v of x minus v of y cubed has to, if I do an integration, this is for y very close to x, and so if I do a integration, then it will be proportional to the linear to a linear power of x, and from here it is just takes 2 minutes. Write it down carefully, so I'll just tell you what to write, and then you can, so this v alpha x minus v alpha 0 into v beta x, if I want to be absolutely finicky about what I have got, and then it is this, and it is v gamma x minus v gamma 0. This is then equal to some constant times epsilon times the structure would have to be delta alpha beta x gamma plus delta alpha gamma x beta plus delta beta gamma x alpha. So that's the structure of this chap over here. You can, given the structure over here, now a couple of contractions and this and that, and eventually what you should be. So try play around with a couple of contractions of this. For example, set beta equal to gamma and sum. That should give you answer, and then that which you can relate to what you have over here. And then you can thereafter, that would set your scale, and the answer finally would be that V alpha x minus V alpha y, this cubed over here, or let's say V alpha r, V alpha 0. This is minus d over d plus 2 for 12 rather 12 over 12 over d epsilon r. So just a little bit of fooling around with taking contractions and so on and so forth, and out comes the Kolmogorov's 4/5 law in d equal to 3, d greater than 3, that's the answer. So d comes from these contractions over here. So delta alpha alpha in a d-dimensional space is d, and if you set d equal to 3, it is 5, and that's the 4/5 law. So this is the answer. This is exact, as I said. Nothing has been invoked except this anomaly over here, that you can take the limit. You have an expression which is this expression over here. This you have derived in bona fide techniques, and then you have looked at the limiting process in two different ways, and in looking at it in one way something has happened, in another way something else has happened. You have made a statement that the velocity field has a non-differentiable at some level structure, and put the two together to get this answer over here, which is closely tied to what are called anomalies in field theory. The anomaly over here, forgetting, is the question of the velocity field having a non-differentiable structure at some level or other. So this is it. I mean, this is the only thing that can be done with confidence, and I'll take just 5 minutes to finish off the story which remains to be told, and that story has to do with the fact that this whole business had this constant flux. All this Kolmogorov business has a constant energy flux going through different scales. Now, is it true? Is it true that there is this? Now, the first argument against it traditionally goes to Landau, who said that, look, let me define what is called a local dissipation. At every point in space, there is the question of local dissipation, which I can define as limit v tending to 0, integral 0 to v d3r del v alpha del x beta del v alpha del x beta. So this is the local, so this is integral. This integral is over a sphere centered at x. So centered at x, you take a sphere, you calculate this quantity over here, and you should get an answer. And what we have just gone through saying is that this answer should be a constant. So this answer should be a constant. Question is that is it? So is this going to be, so the whole you take this at different scales and you calculate this at different scales. So epsilon is supposed to be scale independent. A point which you can see very nicely from here actually, I'll remove this del p. Dimensionally it is no different from this chap over here, so who cares? So scale x by lambda. So let x go to x prime, let's say lambda x prime. Let t go to lambda to the power alpha t prime. So let's say I do this scaling over here. Now if I scale v lambda to some power v prime, what is the scaling which would remain, keep Euler invariant? So you ask the question, what's the, so you put this in, you have lambda to some v prime dot, and this is lambda to the power alpha over here, plus there is v prime square essentially, and there is, that is, and lambda to the power 2 times whatever this is divided by lambda to the power 1. If the equation is going to remain invariant, then I must have these two terms equal, that is lambda to the power this into lambda is equal to lambda to the power 2 times this plus alpha. So 2 times this is equal to, so 1 times this is equal to 1 minus alpha. So the velocity has to scale by 1 minus alpha in this situation, and therefore if the velocity scales by this amount, then your Euler equation would remain invariant. Now let's look at the energy scale. Epsilon r is v cubed over r. That's the local dissipation. Local dissipation would go like v cubed over r dimensionally. So that should go as lambda to the power 3 minus 3 alpha v prime cubed divided by lambda times r prime. So that is lambda to the power 2 minus 3 alpha v prime cubed over r prime. If you want the scale independence, so epsilon at scale r equal to epsilon at scale r prime, then you must have this factor equal to 1, and that forces lambda alpha equal to 2 by 3. So all this Kolmogorov business that we have talked about has to do with this scale invariance, and as I said, that means that the Kolmogorov picture where gives alpha equal, and as soon as you have alpha equal to 1 by 3, 2 by 3 here is v scaling as lambda to the power 1 by 3, which is the length scale. Therefore the Kolmogorov answer that delta v goes like r to the power 1 by 3. V prime, which now goes, which I now go v, which is lambda to the power 1 minus alpha, and then it is this del x square of the del square v, and it is lambda to the power 2. And so it is nu prime is lambda times lambda 1 minus alpha minus alpha minus 1, which is lambda to the power, so alpha was 1/3. What did I do? So v prime was, it is lambda to the power 1 minus alpha, and it is 1 minus alpha, then it is delta x prime square, and it is lambda square, so it is minus 1 minus lambda, and that has to be, this has to be, so this is, all right, so this is lambda minus alpha minus 1, which is minus 5/3 over here, times v prime del prime square v prime square, which is del v prime del t prime, but then with a lambda to the power 1/3 over here, and this is lambda to the power 2/3 over here. So del v, and there is this nu prime going over here. So del v prime del t prime is nu prime times dels, provided this this one minus 5/3 plus 2/3 minus 1/3, that is equal to 0. So this is, this quantity is 4/3. So nu prime, nu goes to nu prime times lambda to the power 4/3, which means that your viscosity has become scale dependent. So you can talk about effective viscosity in these situations, which often goes by the name of turbulent viscosity, which is scale dependent and increases with scale size, becomes very big. So this is the diffusion of momentum. So here is a rough and ready argument for why the diffusion of momentum can increase. So we started out by saying the diffusion of sugar in your coffee pot increases. While we have not handled that at all, there is some other diffusion which increases, and arguments like this are going to get you some answer to start out with. But then, as I said, it is the large deviation problem, and once again, which Sanjib started out with, as that you have the tails of this distribution, which are a big problem. And one of the, what changes too is, you can look at the story in two different ways, that then this whole cascade process remains misunderstood or not understood well enough. And number two, the clearer coming together of theories of large deviations and the dissipation process over here should be could be some kind of a way forward. So that's the story, but the cascade process, which I have just touched on, essentially Samriddhi will have a lot more to say about that, so that will give you a much nicer picture of where one stands and what one knows with confidence and what one doesn't know. So that essentially brings this set to a close. I would certainly like to thank very strongly Abhishek and Sanjib for giving me the chance to talk about things which one generally does not get a chance to talk about ever. So thanks once again, and thanks for being a very alive audience. So thank you very much.